So having seen a variety of algorithms for shortest paths on weighted graphs, we now move to a completely different problem, that of computing what is called a minimum cost spanning tree. So to motivate the problem, let's consider the following example. Suppose we are in a district which has a road network, and after a bad cyclone, the roads have all been damaged. So the first priority of the government is to restore the roads so that relief can be sent to various parts of the district and also people can start moving around again. So the priority is to restore enough roads so that everybody can move around. So the first criterion for the government to restore roads is to ensure connectivity. So given this, which set of roads should the government restore first? So if the main criterion is minimum connectivity, then it should be clear that there is no point in restoring roads which form a loop. For instance, supposing we restore all these 4 roads, right? Then we could have deleted any one of these roads, say 3 to 4 or 2 to 3, and still one can get from any of these 4 towns to any 4 other towns in the district, right? So removing an edge from a loop cannot disconnect a graph, and our aim is to find some subset of edges within this graph which are connected in such a way that this is a minimal such set of edges. So what we want is a connected subgraph of this original graph which doesn't have any loops, which is acyclic, and this is precisely what is called a tree, right? So a tree by definition is a connected acyclic graph, and in particular we start with an arbitrary graph and we are looking for a tree which sits inside that graph, which is a subgraph in terms of the number of edges, which connects all the vertices in the original graph. So such a tree is called a spanning tree, right? It spans the vertices of the original graph, but it forms a tree out of a subset of the edges. So in this graph, for instance, one spanning tree we could form are the red edges shown here, 1 to 2, 2 to 3, 3 to 4 and 4 to 5. Of course, we could form other spanning trees, for instance this green one, which is 1 to 3, 2 to 3, 2 to 5 and 4 to 5. Right? So there are many possible spanning trees that one can construct on a given graph. Now suppose that the graph also has weights. In this example, the weight, for instance, could be the cost of repairing a road. So supposing restoring a road has a cost, and now the government would like to not only restore connectivity, but do it at a minimum cost. Right? So if, for instance, the government chose to repair this tree of roads, then the total cost is 18 plus 6, 24 plus 70, 94 plus 20, 114. So it would incur a cost of 114 to restore this spanning tree. On the other hand, if the government chose this green spanning tree, then the cost reduces to 10 plus 6 is 16, plus 20 is 36, plus 8 is 44. Right? So different spanning trees now will come with different costs, and the goal would be to reduce the cost to the minimum. In this particular example, you can check that this green tree, which has cost 44, is actually the minimum cost spanning tree on this particular graph. So before we move ahead to algorithms to compute minimum cost spanning trees, let us look at some basic facts about trees. So remember that by definition, a tree is a connected acyclic graph. So the graph in general will have n vertices. So the claim is that any tree has exactly n minus 1 edges. Right? So this is very easy to prove. There are many different ways of proving it, and here is one way of thinking about it. So supposing we have a tree, right? So initially the tree is connected by definition. So the entire graph forms one connected component. Remember that when we did breadth first and depth first search, we said that we can take a node and look at everything connected to it, and it forms a connected component. So this tree defines one single connected component if we look at it as a graph in isolation. Now, because it is a tree, if I have an edge from I to j, right, there cannot be any other path going from I to j by some other edges, because if not, that path plus this edge would form a cycle. Right? So if there is an edge from I to j and I remove it, then by definition this component containing I and the component containing j must get disconnected. So if I started with one component, now I get two components. Right? So I delete the first edge from the graph from my tree and I have one component more. Now I delete one more edge. By the same argument, whichever component that edge belongs to will split again. So each time I delete an edge, I increase the number of components I have. But then I know that in the end, if I have n isolated vertices, I can have at most n components, right? I cannot have more than n components if I have n vertices. So I can only do this deletion n minus 1 times, right? So I start with a tree, I keep deleting edges until everything is disconnected. I can only do this n minus 1 times, and I must do it n minus 1 times to get everything disconnected. Therefore, the tree must have had exactly n minus 1 edges. Now, if I take a tree and then I add an edge, it must create a cycle. We already saw this in the previous argument that we said. So supposing I have a tree, right? So a tree in general looks something like this. So it is a graph which has kind of no cycles but many things branching out. Now if I create a tree, supposing I add an edge, supposing I take some I there and some j here and I decide to add an edge, right? So we know that because it's a tree, there is already a connection. So there is some path, which in this case through this vertex from I to j. So for that path p plus this edge forms a cycle, right? So in a tree, I have exactly n minus 1 edges, and when I add any extra edge, no matter which edge I add, it will definitely form a cycle. So another consequence of all these definitions is that between any two paths, any two vertices in a tree, there can only be one unique path. So supposing there are actually two paths. So let us look at two vertices here. We have drawn them as I and j, and suppose there are two paths, right? So if I follow the two paths, okay, then it's very clear that because there are two different ways of going there will be some loop somewhere in between. Okay, so notice that it need not be a loop including I and j, it could be somewhere in between I and j, but if you consider all the cases carefully, you can convince yourself there is no way to have two distinct paths from I to j without creating a loop. And if we have a loop, then the graph is no longer acyclic, so it's not a tree, which is our assumption to begin with. Right? So we have actually the following claim that if we have these three properties, that G is connected, G is acyclic, and G has n minus 1 edges, then any of these two imply the third. So if G is connected and G is acyclic, by definition it is a tree, and we have just shown in the first argument that any tree has n minus 1 edges. So the fact that the first two imply the third is what we have already shown. Now you can easily convince yourself or find a formal proof that if G is acyclic and has n minus 1 edges, then in fact it must be connected. Everything must be connected to everything. And finally, if G is connected and it has n minus 1 edges, then it can only be an acyclic graph. It cannot have any loops. Right? So these are various ways of looking at trees, and sometimes we will use one property or another property. So it's useful to keep these things in the back of our mind when we talk about trees in general. So our target right now is to build a minimum cost spanning tree. So there are two natural greedy strategies that one can think of. One is, since we are looking for a minimum cost tree, to start with the smallest edge and incrementally build the tree. So we keep adding edges to the existing tree so that the new graph remains a tree and it grows as little as possible in terms of cost. This will give rise to an algorithm which is called Prim's algorithm. It will also turn out to be very similar to Dijkstra's shortest path algorithm with a single source. The other strategy we can have is to look at edges in ascending order of cost and keep adding them so long as we don't violate the tree property. Now this is different from Prim's algorithm because here we don't build a tree to start with. We keep adding edges so that we don't create a cycle, but we could have disconnected groups of edges, but eventually they will all connect up to form a tree. So we will see these in more detail in the next two lectures, but let's just look at an intuitive example of how these two strategies work. So let's look at these two algorithms intuitively. We'll come to them in more detail later. So let's start with Prim's algorithm. Remember that the strategy in Prim's algorithm is to start with the smallest weight edge and then incrementally grow a tree. So we start with the smallest edge here, which is the edge weight 6 between 2 and 3. Now we have to look at the existing tree, which consists of this part of the graph, and decide whether to add one of these 4 edges to extend it. We can't add that edge over here. We cannot add this edge because it would not form a tree. It would be disconnected from this edge. So we can add any of these, but we choose the smallest one. So in this case, we choose the edge with weight 10. So the next step in the tree is to add the edge 1, 2, and now we have this tree. Okay. Now if we look at the possible edges that we can add, we have this edge, we have this edge, and we have this edge. Now the smallest among these is the edge with weight 18, but if we add that, we get a cycle. right? So this is not a good edge to add. So therefore we must add one of the other two. Again, we pick the smaller one, which in this case is the edge labeled with weight 20. So then we get this tree which has now this shape. Right? So this is our given tree. Now we can add, we can't add this, we know. So we can either add the edge 70 or the edge labeled with weight 8. And obviously 8 is smaller. So finally we add that, and this is the tree that we get. Right? So this is the final tree that we get from Prim's algorithm by starting with the smallest edge and incrementally growing the tree. The other strategy we said was to start with the edges in ascending order. So we start with the edges with 8, then 8, then so we have, this is the first one, this is the second one, then this is the third one, and so on. So we consider the edges in this order: 1, 2, 3, 4, 5, and 6. Right? So we have the weights 18, 20, and then finally 70. So we have these 6 edges, and we consider them in this order. So among these, of course, the smallest is 6, so we add that. So this is the start of our tree. Now the next one is 8, and that doesn't form a cycle. It doesn't violate a tree property. So we add that. So notice now the crucial difference between Prim's and Kruskal's algorithm. At this point, we don't have a tree. We have two separate trees in some sense, or we have two different acyclic components within this graph, which are not connected to each other, but we are just going in order of edges. So next we see that 10 is the next edge that we can add. It doesn't form a cycle, so we add that. So in some sense, we have grown this component and left that component alone. Now the next one would be 18, but if we add 18, it would form a cycle. So we skip 18, we move to the next one, which is 20. 20 is fine, and 20 will in fact connect the two components and form a tree. So we add 20, and now we are done because we have added n minus 1 edges. There are 5 vertices, we have added 4 edges, and therefore we have definitely got a tree.